Hi, welcome to the other lecture. Today we're going to discuss on orthogonal basis, orthogonal projection, and applications. Be presented to by Dr. Mwijande. I pass you through the orthogonal and orthonormal basis, coordinates relative to orthogonal basis, orthogonal projections, Gram-Schmitt's orthogonalization, and the QR decomposition. Definition. Let V be an inner product space. A set S with the vectors say v1, v2, vk of non-zero vectors is called orthogonal if the inner product of vi, vj is equal to 0, for I is not equal to j. That is to say, if you choose two independent vectors, say v1 and v2 in S, then you take the inner product of the v1 and v2, the solution becomes 0. If that is the case, then v1 and v2 are orthogonal. It is also called orthonormal if, in addition, the norm of the I is 1. That is, for example, the norm of each v1, vi, say v1 is 1, or the norm of v2 is 1, then we say the set S is an orthonormal set. Coordinate relative to orthogonal basis. Let S be the vectors v1, v2, vn be orthogonal bases of an inner product space V. If U is in V, then we can say U can be written as some linear combination of all vectors in S. Now, taking the inner product of U with any vector, say Vj, we obtain the inner product of U with Vj. This can be deduced to be equal to some constant Ci, Cj, inner product of Vj, Vj. Therefore, if you make Cj the subject, you can note Cj is equal to the inner product of U and Vj divided by the inner product of Vj, Vj. This formula here will enable us to find or to calculate the coefficient of the Cj in this formula. Like for example, you want C1, you put 1, put j is equal to 1 here, so we have U V1 over V1, V1, similar to C2. If S with some vectors V1, V2 is an orthogonal basis for V, then every vector U can be written as some linear combination, as I said before, but in shorthand it can be written as U is the summation of inner product of U, Vi, divided by Vi, inner product of Vi and Vi times Vi for all I is equal to 1 up to n. This way of presenting is similar to this one. The difference is that the definition of each Ci has been given in terms of Cj, like this one. Now, if S is an orthonormal basis, then the norm of the I is 1. You can see this term here become unit if this set is an orthonormal. So the formula becomes like this one. Orthogonal projection. Let V be a non-zero vector in an inner product space B, V. We wish to compose Y, which is in V, as y is equal to alpha v plus z, where z is perpendicular to v, or is a member of the complement. Since z and v are orthogonal, it implies the inner product of v and z is 0. Now taking the inner product to both sides with v, that is to say, we use y, we take the inner product of y and v, or v and y, that is v and y, with the y being defined as alpha v plus z, this one. This gives you, this is the inner product in the second argument. This is inner product of v and alpha v, this one, v and z, this one, but alpha can be factored out, so we have this one. But we know v and z are orthogonal. Since v and z are orthogonal, this gives you 0. So we have alpha, inner product of v and v, is equal to inner product of v and y. So you can make alpha the subject. We consider this term alone and this term alone. We have the alpha is equal to inner product of v and y divided by inner product of v and v. Well, since alpha is known, then pictorial you can present like this one. That is the projection of y onto v. This is a vector v, but a portion of this vector v, a portion of this vector is, say, alpha v, this small vector here, the point P, because OV is parallel to OP. So it's logical to write alpha v, OP is equal to alpha v. And suppose we have a vector which is perpendicular to v, say, call it z, here it's 90 degrees. So this one, you can note that now. If you need, for example, the definition of y, you can add this vector OP plus OP or alpha v, this vector plus this vector z. In fact, the answer becomes y. So y becomes equal to alpha v plus z, which is this one. But we know, suppose there's a sun here, so the shadow of y, this line, in fact, onto the screen, say, of v is this shadow, or p, which is alpha v. So the projection of y onto v is alpha v. The only issue was just to know what is alpha. In fact, we have already known alpha is this one. So if this is the case, then we can just substitute here alpha to get the projection of y onto v is alpha v, which is, this one is alpha, which is alpha v. So the projection of y onto v is this inner product of v and y divided by the inner product of v and v times vector v. The component of y orthogonal to v is z. You can see from this diagram the component, the vertical component is z, this one is z. You say the component of y, y orthogonal to v is z, is this vector z, which in fact z could be written as, from here you can see this is the projection plus z equal to y. So you can say z is equal to y minus projection of y onto v. So else you can write y is projection of v plus y minus projection of y. This is y. So Now, let us talk of projection onto a vector space. Now, suppose W is a subspace of V with some orthonormal basis V, or orthonormal basis beta with the vector V1 to Vk. Now, for Y in V, the projection of Y onto W is projection of Y onto W is a summation of inner product of Vi and Y divided by Vi times Vi. You can note that it looks like an extension of the individual projection of a vector V onto Y. In the beginning, it was only a single vector V1 or V here. That's why we have V here, V here. But if there are so many of them, so many vectors that form the basis, say V1, V2, V2, V1, V2 up to Vk, then the formula changes. It extends to the summation of the individual's projections. That is the projection of V1 onto Y and projection of V2, you add them, V2 to Y, etc. That is the way. So this is the projection of Y onto W, where W is a subspace of V. The orthogonal complement, as usual, we can say Z, which was Z. Z will be equal to Y minus projection of Y onto W, where we know this one is a vertical component, so we can say this is a member of omega complement. So if beta is an orthonormal basis, then we cannot, as you said before, if beta is orthonormal, the norm of this vector Vi become 1. That's why I can see the formula changes to this one. Now we can try to see some example on how we can really compute the projection of a vector onto a subspace. Now consider the vector, say V1, V2, V3. These are vectors which are in a subspace, say W. So we can check whether they are orthogonal. Let us check if this is a orthogonal basis. The inner product of V1 and V2, if this one is standard Euclidean space, V2, this one is 0. So V1 and V2 are orthogonal. Okay, now the vector V1 and V2 are orthogonal. Our aim is to project the vector V onto these bases. If V is the vector 1, 0, 0, so we want to project a V onto these bases W. So we can say, since the formula for projection onto Y of V onto a subspace is just the individual projection of vector V1 on the V1 onto W. So V1, inner product of V1 and V times V1, and inner product of V2 with the V times V2. So this one is the formula. So on computation, will give you, let's just compute a V1V. In fact, this is 1. V1V1 is 6, and V2V is 1. Inner product of V2, V2, this is 3. So just substituting that formula here, and really you obtain the thing here. So projection of V onto W gives you a half, 0, and a half. That's all about projection of vector onto a vector space or a subspace. Now, let us stop there. Next lecture, we shall discuss with you the Gram-Schmidt orthogonalization process. Thank you.